Absolutely great paper for making large language models efficient. A look at low-array fine-tuning aware quantization or LoftQ. LoftQ shines in natural language tasks, NLU, QA, summarization, and NLG. Outperforming existing methods, especially in the tough 2-bit and 2/4-bit mixed precision realms. Elevate your model's performance with LoftQ. This paper tackles the performance gap in quantization plus LoRa fine-tuning. Witness a remarkable boost in downstream task performance, closing the gap between quantization and full fine-tuning. Large language models, LLMs, have revolutionized NLP, but their massive size presents a challenge for practical deployment. Quantization, a technique that reduces the precision of model parameters, offers a solution. However, applying quantization while fine-tuning LLMs using low-rank adaptation, LoRa, can lead to performance degradation. In this post, we explore LoftQ, a novel quantization framework that addresses this issue, allowing efficient fine-tuning of quantized LLMs without sacrificing accuracy. The problem: quantization and LoRa don't always play nice. Quantization aims to shrink the memory footprint of LLMs by representing parameters with fewer bits. For example, 4-bit quantization can reduce storage needs by 75% compared to the standard 16-bit format. LoRa, on the other hand, enables efficient fine-tuning by adding small, low-rank matrices to the pre-trained model's weights, keeping the original weights frozen. The issue arises when combining these techniques. Quantization introduces discrepancies between the original and quantized weights, particularly in low-bit settings like 2-bit quantization. This disrupts the LoRa initialization, leading to suboptimal fine-tuning performance and even convergence failures. LoftQ, bridging the gap with low-array-aware quantization. LoftQ tackles this challenge by jointly optimizing the quantized model and the LoRa initialization. Instead of simply quantizing the pre-trained weights and attaching LoRa adapters, LoftQ minimizes the difference between the original weights and the combination of quantized weights and LoRa adapters. This ensures a better starting point for fine-tuning, leading to improved performance on downstream tasks. How LoftQ works: an alternating dance of quantization and SVD. LoftQ employs an alternating optimization approach that iteratively refines the quantized weights and LoRa adapters. Quantization: the difference between the original weights and the current LoRa approximation is quantized, generating updated quantized weights. SVD, singular value decomposition, SVD, is applied to the residual, the difference between the original and quantized weights, extracting low-rank approximations to update the LoRa adapters. This process is repeated for a few steps, effectively minimizing the gap between the original and quantized models and providing a strong foundation for LoRa fine-tuning. Putting LoftQ to the test, experiments and results. LoftQ's effectiveness is demonstrated across various NLP tasks and model architectures. NLU tasks with DBRTAV3, LoftQ consistently outperforms QLoRA, a baseline method combining quantization and LoRa, on tasks like MNLI and SQADV 1.1, especially in challenging 2-bit quantization scenarios. Summarization tasks with BART, LoftQ achieves significant gains on XSUM and CNN/DailyMail datasets compared to QLoRA, even surpassing full precision LoRa in some cases. NLG tasks with Llama 2, LoftQ exhibits superior performance on Wikitext 2 and GSM-8K datasets, demonstrating its ability to handle decoder-only models and mixed precision quantization settings. These results highlight LoftQ's versatility and robustness in low-bit quantization regimes, making it a valuable tool for efficient deployment of LLMs. Advantages of LoftQ: efficiency, accuracy, and flexibility. LoftQ offers several benefits over existing methods. Improved accuracy. By minimizing quantization discrepancies, LoftQ unlocks the full potential of LoRa fine-tuning, leading to better performance on downstream tasks. Reduced memory footprint. LoftQ enables significant model compression through quantization, facilitating efficient deployment on resource-constrained devices. Flexibility. LoftQ is compatible with various quantization methods and LLM architectures, making it adaptable to different scenarios and needs. Computational efficiency. The alternating optimization process adds minimal overhead, and the training cost remains low thanks to LoRa's parameter-efficient nature. Also, now, let's understand the role of SVD in LoftQ. Singular value decomposition, SVD, plays a crucial role in LoftQ by efficiently extracting low-rank approximations from the residual matrix, which represents the difference between the original pre-trained weights and their quantized counterparts. This low-rank approximation is then used to update the LoRa adapters, ensuring a better initialization for fine-tuning. Let's delve deeper into the workings of SVD and its contribution to LoftQ's success. SVD, decomposing matrices for low-rank approximation. SVD is a powerful matrix factorization technique that decomposes any matrix into three matrices. U, a matrix with orthonormal columns, capturing the important information about the rows of the original matrix. Sigma, a diagonal matrix containing the singular values, which represent the importance of each component in the decomposition. V to the power of T, a matrix with orthonormal rows, capturing the important information about the columns of the original matrix. The key property of SVD is that it allows us to approximate the original matrix using only a subset of its components. By selecting the largest singular values and their corresponding columns in U and V, we can obtain a low-rank approximation that captures the most significant information while discarding less important details. SVD in LoftQ, bridging the gap with LoRa adapters. In LoftQ, SVD is applied to the residual matrix, which is the difference between the original pre-trained weight matrix, W, and its quantized version, Q. This residual represents the information lost during quantization. By decomposing the residual using SVD, LoftQ identifies the most crucial components of this lost information. The resulting low-rank approximation from SVD is then used to update the LoRa adapters, A and B. These adapters are responsible for adjusting the model's behavior during fine-tuning. By initializing them with the key information extracted from the residual, LoftQ ensures that the fine-tuning process starts from a point that is closer to the original pre-trained model, mitigating the negative impact of quantization on performance. Why SVD adds value in LoftQ? The use of SVD in LoftQ brings several advantages. Efficiency. SVD provides an efficient way to extract the most important information from the residual matrix, allowing for a compact representation using low-rank adapters. Accuracy. By preserving the crucial aspects of the lost information during quantization, SVD helps to bridge the gap between the original and quantized models, leading to improved fine-tuning performance. Targeted adaptation. The information captured by the SVD-based LoRa adapters is specifically tailored to compensate for the discrepancies introduced by quantization, leading to more effective fine-tuning. SVD, a key ingredient in LoftQ's recipe for success. In conclusion, SVD plays a critical role in LoftQ by enabling the extraction of essential information from the quantization residual and using it to initialize LoRa adapters. This approach effectively mitigates the negative impact of quantization on fine-tuning performance, paving the way for efficient deployment of large language models without sacrificing accuracy.